This conference will now be recorded.
Very good evening, students. So we have been discussing electricity and current. So we had somewhat discussed about electrolyte cell yesterday, and we were discussing series and parallel combination of electrolyte cells. So today we'll go a little more deeper in discussions of series and parallel combination of cells. So I'll just recap what we had discussed yesterday, a little bit about this cell. See, an electrolyte cell consists of two metal electrodes. One is actually having at positive potential, another one is at negative potential, and those electrodes are dipped into the electrolyte. Actually, what happens initially, there may not be any potential or any polarity of these electrodes, but these electrodes are so chosen that as soon as they are dipped into the electrolyte, there will be charge transfer. There will be charge transfer from electrolyte, like through electrolyte. Okay, through electrolyte there will be charge transfer, and one will be at positive potential, another will be at negative potential. Now, if we see in this case, like this is a positive at positive potential, this is negative potential. So the point in the electrolyte A and B. So the potential difference between this A and B, VA and VB, we had seen yesterday. That will be if we obviously see in the open circuit condition, if this external resistance is not connected to this electrodes, then the potential difference between the electrodes is called the electromotive force that we have already discussed, and that electromotive force is denoted by E. So EMF in short, electromotive force. Electromotive force, EMF. I'll just repeat it. So in open circuit condition, when we measure the potential difference between these electrodes, that is actually EMF. Now if we connect these electrodes with an external resistor, then what happens? There will be a flow of current because of the flow of charges in the external circuits. Okay, so suppose I, as you see, suppose I is the current flowing through the external circuit and in the direction C to D. So in the direction C, or we can say P to N, in the direction P to N, current is flowing in the external circuit. But to close the circuit, see inside also there will be flow of current, and the same current in fact, and the direction of the flow of the current will be N to P. That means negative terminal to positive terminal. Okay, and as you know, since there is electrolyte material, it is actually not perfectly or 100% conducting. Obviously this electrolyte will offer some resistance to the flow of the current, and that resistance is called internal resistance and denoted by small r. Okay, that is denoted by small r, internal resistance. Okay, and this, as I said, this is external resistance. All right, so this is the thing. Okay, so at this condition, when the electrodes are connected to the external resistor, at this condition, what will be the potential difference at potential difference between P and N. so that I can find out like this also. See, you know, this V is actually, I can say, the potential difference between potential difference across the R also. This could be said as well. Okay. So this will be, you know, already see, if there is internal resistance in the electrolyte, or this is called internal resistance of the cell, then already some potential drop will be happening between this AB, actually between this AB before it reaches to this. In fact, I could, let me okay, so potential difference will be here, you know, so V E minus IR, sorry, this is smaller, this will be smaller, so V minus smaller, sorry, I minus smaller, this is the drop. See, open circuit condition, it will be able to give the whole potential difference, but when there is a flow of current inside the electrolyte also, there will be a drop. This is actually potential drop, or internal, this is called actually worst voltage also, it is sometimes said. Okay, this is actually lost voltage, you can say, or worst voltage, lost voltage maybe we can say. Okay, so this is lost, actually lost due to internal resistance of the cell, internal resistance of the cell. Okay, a drop of the potential also you can say. Anyway, so this is one term, so this will be subtracted from the total EMF, and that will be the voltage drop across this R, or the voltage drop or potential difference between the electrodes when it is connected to the external circuit. And see, circuit symbol, you can see this is the circuit symbol of the battery, like this. Okay, this is the thing. Okay, so far we have learned this. Now we'll go to the series combination of cells. Combination of cells, there are two types as I discussed yesterday. So first we will discuss series combination. Series combination, we had little bit discussed about it, but we'll discuss in detail today again. Series combination of cells. Okay, suppose I have two cells having EMF E1 and internal resistance R1, and the other one is having EMF E2 and internal resistance R2. Okay, now we have to find out. See, I have three points A, B, and C. I have to find out equivalent. That means, see, obviously, you know, see, sometimes we may need very high potential for an experiment or for some requirement. So a single cell may not give you the same thing. So we need to use a number of cells to get the same amount of potential, to get the required amount of current through the circuit. So in that case, we will be using this combination of cells, and combination of cells also called battery. Okay, so you look here, this is the equivalent circuit. Suppose I need this much equivalent amount of potential, which should have equivalent amount of resistance Req. Okay, out of these two cells. So when we say series combination, so when the negative terminal of one battery is connected to positive terminal of the other battery. Okay, this is actually series combination. Okay, so suppose it has EMF U1 and it has E2, we will see that they will be simply added. But if I have positive terminal like this, then again negative terminal, then positive terminal, then also it is series combination. But if this is E1 and this is E2, so combination will be negative. I'll show you here. After calculation, we will just discuss these circuits. Okay, so let me assign. Okay, we need to find out actually the voltage difference. See, in this case, one thing is very important, that in any kind of series, whether in a series of capacitor or series of resistor or whatever it is, so current will be same in the circuit, or current will be same through all the components, circuit component. Like here, current will be same through the battery cell E, and through the cell like cell 1 and cell 2, you can say. So current will be the same in the circuit in the case of series. All right, and I know this internal resistances. So let me check what is happening here. So here, one thing is that the total potential difference, see VAC, this I can write as the potential drop across AB, like across this cell, okay. Let us see potential here. So VAB plus VBC, okay. So this is the total potential. Now we have to see what is VAB. So we have already seen for a cell, what we have seen just here, we have seen the V for a cell is E minus I into R. So that we will be using here. Okay, that knowledge will be applying here. So VAB, what we can write, VAB means across this, okay, for this cell. So I can write VAB as E1 minus IR1, okay, plus this we can write E2 minus IR2, right? So this I can write as E1 plus E2 minus of I R1 plus R2. Okay, so this is VAC. Suppose I draw an equivalent circuit for this particular series combination like this, then for this, see, for the same potential difference, VAC, what I can write here, E equivalent minus I for the same current, okay, same current and same potential difference across the cell. I can write this like this. So if we compare this equation and this equation, we'll get the equivalent EMF of the batteries in series and internal resistance also. So look, this comparing equation 1 and 2, we get U1 plus E2, and R equivalent will be R1 plus R2, right? So these are two things we have got. So you can see in case of series combination, the EMF, equivalent EMF is just additive, and also equivalent resistance, internal resistance, will be just additive in the sense, you know, like this is series combination of internal resistance, kind of series combination of internal resistances. Okay, so this is the thing. Now let me discuss about these two figures. So what I have said here is that if See, series combination here, suppose R1, R2 are the internal resistances. So in this case, what will be the equivalent EMF? Equivalent EMF for this circuit will be E1 plus E2. But for this one, what will be the case? It will be E1 minus E2. Why? This is in opposite polarity. This will be with minus sign. This is in opposite polarity. Okay. So this is the thing. So this is what I just wanted to say, that when in series also, if the batteries are or cells are connected in opposite polarity, we have to take the right polarity to find out the equivalent EMF, okay, of the circuit. So this is the thing we have to remember. But one thing is very, very important to learn, that the resistance, they don't have any polarity, right? So this R equivalent will be always R1 plus R2. It will be just additive, just series combination of internal resistance. Okay, this is what we need to know from the series combination. Now look, if I go for series combination for an n number of cells, for an n number of cells, let me write series combination of n cells. Okay, so I have n cells, say I'll just draw a figure like this: positive, negative, then positive, negative. I'm just taking a general case: positive, negative, like that. It goes up to n cells. Okay, and let us say there is an external resistance connected to this. This is capital R, and each of them has, suppose for the time being, I say all of them are having same EMF E. N cells of same EMF and same internal resistance R, say same internal resistance R. I will just write here N cells having same EMF and internal resistance. Okay, all right. So in this case, suppose I have to find out the condition for maximum current. Condition for maximum current. Here what we are going to study: condition for maximum current. What is this? We'll just discuss as we go along. Let me first find out what is the current first in the circuit. How do you get the current? Current in the circuit, let us say that is I. So total EMF of the circuit, right? Total EMF of the circuit and total resistance divided by total resistance. Total resistance. So that is the current. So what is the total EMF here? There are n such series. See, if I add E plus dot go up to n number of cells. Okay, there are n number of cells. Okay, n number of cells like this. Okay, n term. So it will be n into E. Total EMF will be n into E, right? And each of them has this internal resistance R. So what will be the total internal resistance? Total internal resistance R prime will be NR. I hope you agree with me. So then total resistance in the circuit will be, see, total EMF we have got N into E divided by total resistance will be external circuit resistance in the external circuit plus NR. So this is actually the total current. Now this current will be when it will be maximum and when it will be minimum. So there are two conditions we will see when it will be. First of all, when it will be maximum. What is the, see, in the case of cell, I don't have any choice. Okay, I have been given the cell. Now what I have choice is with this external resistance. I can use more than, see, I will just take first condition. First condition, say this external resistance is much greater than internal resistance. We'll see what will be the current in this case. If this is the case, look what will happen. Then the NR can be neglected. NR can be neglected, right? Internal resistance can be, sorry, yes, the internal resistance can be, this can be neglected, isn't it? If we neglect this, then what we can write? See, this we can write NE by capital R, right? So the current will be NE by R. So what is this N? N is a factor, number of cells, and see, E by R, this is current due to a single cell in the external circuit. So this is the current in the external circuit. External circuit in short is CKT, circuit due to a single cell, and see, N is multiplied with that. That means what? We are going to get N times the current drawn from a single cell. Okay, N times the current. So we can write here. So in at this condition, see, current will be N into current see, E by R drawn from a single cell. Okay, so this is the thing. So let me go to the next page. Yes, so here we'll see another condition. So condition number 2. So first of all, let me write the total current we had got, this plus this into NR. So this is for combination of N cells having EMF E and internal resistance R. But now the condition is that if R is much less than NR, what is going to happen? At this condition, see, I can write the total current as N into epsilon divided by, see, this is neglected then, so this will be NR, and see, what is this? This is this. So E by small r. And what is this? This is the current given by single cell. So this is the current given by a single cell. Okay, given by a single cell. So what is the conclusion we can draw from this? See, in case, see, I'll write the two cases side by side. So in one case, R is much greater than NR. So in this case, we have got current N into E by R. Okay, the current drawn from the single cell into N. That means you will get the current equivalent to the current drawn from N cells. This is one. And second thing is, see, if n is r is much less than nr. So in this case, what we are getting? This we are getting E by R. That means current which could be supplied by a single cell. So we can draw a conclusion that when when the external resistance is much larger, than the internal resistance, the cells should be connected in series to get maximum current. Okay, so this is the conclusion, that when the external resistance is much larger than the internal resistances, then we should connect those cells in series to get the maximum current. Okay, so these are things. Okay, now we'll go to, okay, so I think let me just go to the next page. Okay, let me just do one thing. Let me copy this figure and go to the next page. Okay, so we'll discuss now parallel combination of cells. Okay, parallel combination of cells. So see the figure, when the like electrodes are connected to a single terminal, and the other two electrodes are connected to some other terminal together, then cells are actually called to be connected in a parallel combination. Okay, now in this case we have to find out what is the equivalent EMF for this combination. So as I discussed earlier also, whatever it is, whether their resistance or their like resistor or capacitor or these cells, whatever it is, since they are in terminals are connected to the same potential, or in other words, since the same potential is across all these components, resistors or capacitors or cells, so in this case, the current will be divided in two branches. So current will be divided into two components. Okay, current will be divided, but the potential will be the same across each cell. So let us, parallel combination of cells. So in that case, what we need to do is, We need to find out the current across, or current what is flowing through each branch and add them to total current. So what do I mean by that? So I is equal to I1 plus I2. This is the thing. So from here we will be able to find out equivalent EMF and resistance also. See, then I will find out what is the current I1. So this is my M. This is my M. So I1 is, see what we know about this cell. See, we know in the previous discussion also we have learned this is IR1, or in this case I1 R1. I1 and R1, both the current and resistance, internal resistance anyway they are different. Okay, so I can write, see, I1 I can write E1 minus V divided by R1. Similarly, I2 can be written as this. Okay, so applying this, we can get I is equal to I1 plus I2, or E1 minus B divided by R1 plus E2 minus B divided by R2. Okay, this is very simple. Now see, if I go for the equivalent circuit, in this case also, if the equivalent cell is connected across the same potential V, and suppose the current is also flowing through this, then the EMF of this cell will be equivalent 1. Okay, so let me write this here also as E equivalent minus V by R equivalent. Okay, all right. This I'll compare with this side. Okay, for the timing, let me find out. Let me find out V itself. Okay, from this, for the time being, let me find out V. What is V? I'll just find out from here. See, I is equal to E1 R1, E1 by R1 plus E2 by R2. Let this be separated, and see here, if I write V, then it will be 1 by R1 plus 1 by R2. Okay, now from here actually we'll be able to do that. Let me write this as E1 R1, sorry, this will be E1 R2, E1 R2 plus E1 R2, E2 R1 divided by R1 into R2. Okay, this part minus, this will be V R1 plus R2 divided by R1 R2 divided by R1 R2, right? So in this case, see, if I bring this I here and get the V, let me do one thing. I'll just multiply this term, like this term, both side. Okay, so we'll come here. So I into R1 R2 divided by R1 plus R2. I'm multiplying with this term everywhere. Okay, so, or maybe we can multiply with minus sign. Okay, with minus sign here, then no, let's skip like this. And this, with this, when we multiply, so R1 R2 will be getting cancelled. So I1 R2 plus I'm just doing a little. Okay, fine, yeah, this fine. Okay, so E1 R2, E2 R1, this is fine so far. Then I'm multiplying with this term, right? This term, that means this R1 R2 will be getting cancelled, whereas here it will be R1 plus R2. Okay, this much we get, and with minus V. Okay, So I want to get V, right? So I'll just go with this. V is equal to E1 R2 plus E2 R1 divided by R1 plus R2 minus R1 R2 divided by R1 plus R2 into I. All right. So in this, look, I was just writing for this equivalent circuit, isn't it? So for this, what we can write? We can write V is equal to, so across A and C, the same potential I have considered and the same current I have considered through the circuit. So you know of what I can write from here. So I can write this is EQ minus IRQ. Okay, look this suppose this is equation number 3, and this, let us say this is equation number 4. So if I compare this 3 and 4, so what we are going to get, see, E equivalent we are going to get is E1 R2 plus E2 R1 divided by R1 plus R2, and R equivalent will be obtained as R1 R2 divided by R1 plus R2. So this is in case of parallel combination, right? So these are, see, one more way is there to express this. We'll just do that. See, if we just divide, if we divide E equivalent with R equivalent, see, for your current information, let me tell you what is this. So this could be written as like this: 1 by RQ is equal to R1 plus R2 divided by R1 R2, right? R1 R2. So this will give you 1 by R 2 plus 1 by R1. That means 1 by R1 plus 1 by R2, isn't it? So this is R1, this is R2. So what does this mean? This means that in parallel combination of cells, the internal resistance will be combined, like they will combine just as the just as the resistance are combined in parallel combination. So in case of parallel combination of cells, internal resistance also will be combined as a parallel combination. Okay, parallel combination. So this is what we have seen here. So from this two, it is very, very evident. Okay, now, so there is a simple way to remember. So this will be, see, if I just multiply this, see what will happen. So this will go in the numerator, this will come in the denominator, and see, this is R2, this is R1. So E1 by R1 plus E2 by R2 we will get for the time being here. Okay, if I have n such cells, then I can just continue with this. U1 by R1 plus E2 by R2 plus E3 by R3 plus dot dot dot, it goes up to En by Rn. So if there is n cells, then I can write in this way. Okay, so so these are few way, like this is equivalent EMF for parallel combination of cells. This is the internal resistance, and this is another way to express this equivalent resistance and equivalent EMF. Okay, so far it is very, very good. Then what we are going to do is we are just going to see if there are n number of such cells connected in parallel combination, then what will be the condition for maximum and minimum current. Okay, so what I'll do, I'll just erase this here, and then I'm going to do one more thing. I'm just going to bring this way. I'm going to write the this formula is there, and I'll just get this room here. So what we have got, E equivalent is this U1 R2 plus E2 R1, okay, divided by R1 plus R2. Okay, this is what it is, and then this is R1 R2 divided by R1 plus R2. This is parallel combination of the cells. And one more formula we have learned here. This is very, very easy to remember. E1 by R1 plus E2 by R2 plus E3 by R3, and this goes up to n cells. Okay, En by Rn. Okay, now let me, okay, I think just a minute. All right, so we'll see condition for maximum current, condition for maximum current, maximum current in parallel combination of n number of cells. Okay, n identical cells, let us say identical cells. Okay, I'll just tell you what it is. Suppose I have, see, I have n number of cells. Okay, like that, there are n number of cells here. Okay, n cells, and identical cells. So these are all identical cells. All right, so see, I have to find out the current, expression for the current, right? Suppose this is the external resistance. So each of them has internal resistance R and EMF E, identical. So this is external resistance. So look, in this case, now at least we can say what is the total EMF? Total EMF. Okay, I'm writing this total EMF. In case of series combination, total EMF, what it was. So when the cells are identical, when the cells are identical, then the total EMF will be the same as E, same as the same. So this will be E. All right, why it is? I'll just put it here and say, see if there are, see if these are EE and the resistance are also same. See ER plus, I'm taking with the 2, so this is also ER divided by R plus R. All right, so see what it is. This is 2ER divided by 2R. So what you get? You get the same, right? When the cells are identical, so what I'm trying to say, when cells are identical, then the EMF will be the same, even if there are n cells connected together. If the cells are identical, if the cells are identical, then total EMF will be this, same as the 1, and the total internal resistance will be how much? Total internal resistance, so that is R prime, say small r prime, and this will be, what, 1 by, say this is R means, let me first do one thing. Total internal resistance 1 by R prime is equal to 1 by R1. So R1, all are actually the same, 1 by R, plus it goes up to n term. Okay, n cells. So that means, like you get n by R, n cell by R, like n by R. Okay, so what will be the internal resistance, equivalent internal resistance? Then it will be R by N. So the total resistance will be total resistance R plus total resistance is R plus R prime. That means what? R plus R by N. Okay, this is the total resistance. So what we get as total current. Okay, let me just write it here. Total current. So total current will be, see, I have total EMF divided by total resistance. So that is R plus N, R by N. Okay, I need this expression, and rest of the things you have already learned or listened. You have already heard of this uh, part, so I can actually remove some of the parts if I require in between. So I need to find out the condition for maximum current and like maximum current in the circuit in case of parallel combination. So that is what we are trying to establish now. See, I'll just remove this part. I hope you have got the figure in your mind now. So I just need what is this expression alone. Expression for the, so this is R equivalent, say. Okay, so we have total current now in the parallel combination of n cells, n identical cells. Current is E by R plus small r by n. Okay, this means what? See, now I'll just apply the condition directly here. If suppose, so first condition is, if R is much greater than a, see, R, then what will happen? Then I'll get the current just as this. Okay, I'll get the current like this. Okay, that means the current drawn from, so this is current drawn from a single cell. Current drawn from a single cell. Okay, this is current drawn from single cell. Now let us take the second condition. If this is much less than R, so what is going to happen now? See, in this case, this term can be neglected. Okay, so we get I is equal to R by N. This is the thing. So this N goes up. So NE by R. That means the current. So this is becoming I is equal to N into current supplied by, or current obtained from a single current, N into current obtained from a single cell. What does this mean? This means that when the external resistance is much less than the internal resistance, okay, internal resistance, then such cells are used in the parallel combination to get the maximum current like this. Okay, when the external resistance in the circuit is much less than the internal resistance, then you should use all those cells in parallel combination to get the maximum current. Now let us go back to this conclusion. What was that? This, see, when in case of series combination, the internal resistance, when it is much higher than the higher than the internal resistance, in that case the cells could be used in the series combination to get maximum current. So here also we'll write this conclusion point. So what is the conclusion? So what is the conclusion? So let me just do one thing. I'll just erase everything. I'll just write the important formula, and then I'll write the conclusion here. I'm not just blessing all this, like cleaning all together. Then the heading also will go. Okay, now I have got, see, I have got formula for the current, total current as epsilon by R plus N by R, right? Sorry, R by N, equivalent resistance. So this is R by N in case of parallel combination. Now I have got two conditions. One is R is much greater than R. So in that case, what will happen? The current will be, see, this will be like this. Okay, and in the condition, see, when the condition is much less, capital or external resistance is much less than the internal resistance. So in that case, you know what will happen? So this will be Ne by R. That means, see, this is actually N times current supplied from, or N time into the current obtained from a single cell. Okay, so the conclusion we'll write here. So what is the conclusion? The conclusion is that when the external resistance is much lesser, when the external resistance is much lesser than the internal resistance, the cells through which the cells, oh sorry, the cells should be, the cells should be connected, the cells should be connected in parallel combination, in parallel combination to get maximum current out of it. Okay, so these are conclusions from this side. Now we'll just learn a very interesting part, that is the mixed grouping. This is very important because there is to be questions from competitive, like question from this topic for competitive exams. So we'll just learn this very well. Okay. So in case of mixed grouping, see here, as you see, there are n cells in a row, n cells in a row, n cells, n cells in series, and column, see column number, see m such rows are, m rows are there, m rows, I'm sorry, m rows, yes, m rows of such series of the cells. That means what? See, I have m rows and n, see, n, sorry, n cells. I have rows like this. I have rows and I have single column, suppose. Okay, in the single column, where how many rows are there? N rows are there. Sorry, M rows are there, and each row has how many cells? Each row has N into E. Okay, I'm sorry, N cells. So total number of cells, number of cells. So N row, or sorry, like a row, a single, like with M rows with one column, and in one column there are N cells. So there will be, see, number of cells will be actually N into M, or Mn, whatever you say. So M rows, and each row contains N cells. Okay, and see, then each row has EMF in each row, EMF in each row, how much? N into epsilon, right? N into epsilon. And when these N, like N cells in a single series, a single row, and there are M such rows. So when M such rows are connected together in parallel, see, in this, the total EMF of this combination will be total EMF of this combination. And I have forgotten to tell you, each cell has same EMF E and internal resistance R. That is the thing. The total EMF will be N E in E, like this itself, because see, I have told you, like, there are identical cells, and see, suppose there are 3 cells are there, and all of them are having same EMF, and they are connected in parallel. Then the EMF of the combination will be EMF of the single one. Okay, so I get total EMF N into E. So what will be the total resistance here? So total resistance. So total resistance will be how much? So each row contains how much? So each row contains NR. Each row NR resistance. Each row N into small r. So how many this, so, and this, see, M, see, there will be, see, 1 by r prime is equal to 1 by NR plus 1 by NR. Such series, see, such okay, such rows are there, right? So there are M such rows. So M such rows. Okay, like this. All right. So this is the thing. Now, so this will be, see, there will be M terms. So I can write M by NR. M by NR. Identical, right? So I can write M by NR. All right. So equivalent resistance, internal resistance will be R is equal to NR by M. So this is the thing. So I can write total resistance, this external resistance plus this R prime, that is R plus N R by M. These are the parameters we have already found out, the parameters, so we can find out now the total current in the circuit. Okay, if we require, we can find out the total current in the circuit, and obviously we will be seeing maximum current condition for this also. Let us go to the next page. So mixed grouping, in case of mixed grouping, we have got total current is equal to total EMF divided by total resistance. So total EMF is how much? We have seen that N into epsilon. And total resistance is how much? We have got R plus NR by M. NR by M. Okay. This is, see, we can just do this again, little bit more simplified form. This is mr plus anr. mr plus nr. So you can see this current has to be maximum if this is maximum. See, this will be maximum when I will be Imax when this term is minimum. This is minimum. Okay. So how to get this as minimum quantity? I'll write this term as this term itself. So this is nr here, n smaller. So we have to make this minimum. When this is minimum in the denominator, then the total current will be increasing. Okay, now look this. This could be written as this could be further written this plus 2 root over m n, this will be r. Okay, I'm sorry, there will be in they are also inside root. So this will be m n r. There will be 2 also. So see, to make this minimum, this should be minimum. But see, if this square is there, always the term will be maximum. Okay, so this should be 0. This must be 0. This must be 0. Square term must be 0. So this will give you actually AMR, and this NR is smaller. Okay, so this is the condition, and you look here, the condition says if this capital R is equal to n by m is equal to m by n. Okay, so this is the condition. So what is the condition we have got so far? The condition is that n r by small m, that is the total. There will be one n also, right? Rn by m. So this is the condition for maximum current to get in a group of cells. I think I'll stop it here. Next day we'll learn a very, very interesting topic, that is actually efficiency of EMF cell, and we'll learn few more things like power in a parallel series combination of bulbs, and then efficiency of EMF cell, and then maximum power theorem. Those things will be learning in the next class. Okay, so thank you for your patience. Bye for today.